Okay, so let's get started as far as topics for this class goes. And so this is Stats XL10. This is Introductory Statistics. Okay, and I love this class. Okay, and I love teaching it. I feel like I've got my dream job teaching introductory statistics or just statistics in general to college students because I love teaching and I love the subject of statistics. And I hope through this course maybe you come into my class with kind of the feeling that you're not really a math person, or you know, whatever else. Maybe you've been wronged by math teachers in the past, and so you don't like the subject or whatever. Well, I hope at the end of the class you'll at least have an appreciation for the subject of statistics. When I took statistics as an undergraduate student, it literally changed my life in that here I am now. You know, I came back, so you know, I started off in engineering as an undergraduate student. After I graduated, I finished my degree in engineering, and then I worked a little bit, but I decided to come back to graduate school to study statistics because I fell in love with the subject of statistics as an undergraduate student. And so here I am teaching statistics, hoping to inspire other students maybe to appreciate this subject. Okay. So maybe first of all, before we begin any course, one question you should ask is why are we taking this class, right? So why do we study statistics? Okay. And for many of you, the answer for why you are in this class is because you need the class to transfer, or you need the class to fulfill some kind of requirement for graduation, or whatever that might be. And that's fine. That's, but then, you know, why is this a required class? Why would this class fulfill the math requirement for transferring or graduation or whatever it might be? Okay. Well, somewhere, someone who makes these decisions, or the people, the committee who makes these decisions, decided that statistics is a worthwhile subject. And I agree that statistics is a worthwhile subject. But of course, I'm biased in my opinion there. But so this is what I argue that statistics allows us to do. So why do we study statistics? So, you know, from a very broad definition, statistics, this subject, helps us gain a better understanding of the world around us. Okay, but you know, this statement that the subject that we are studying helps us gain a better understanding of the world around us can be said about many subjects, whether it's history or political science or biology or physics. All of these different subjects explain some part of the world or the way the world works or whatever it might be, and helps us gain a better understanding. So in particular, okay, what statistics allows us to do statistics allows us to make conclusions from limited data. Okay, so this is probably, I would say this is the key reason why we study statistics. It allows us to make conclusions from limited data. Okay, and I should just check in with you guys and make sure that everything is visible and legible and you guys can hear me and read and write down and everything. Okay, great. Okay, I am, as I take these notes, I save them and I will be posting the notes online as well. Okay, so you know, I recommend taking notes in class. I think it's a good way to learn, but some of you learn better by just sitting and paying attention. And if that's you, that's fine. You can the notes will be posted for you to review. Okay, and I do recommend reviewing the notes. If you take notes and you don't review them, what's the purpose of taking notes, right? So so take notes and then review them as you study. Okay, so you know, allows us to make conclusions from limited data. Why is this even necessary? So generally in science, okay, as we try to perform science, we often have some kind of research question. Okay. And so, you know, for example, and the research question we will often need to define very clearly, and that's like a subject for another class. But you know, we could ask, you know, is some new experimental medication more effective at treating, let's say, breast cancer patients than currently existing treatments? Okay, so this is a question. It's a question that we should that maybe pharmaceutical companies might be interested in if they're trying to develop a new cancer treatment. Okay, and so this would require some kind of study or experiment. Okay, so maybe to answer this question, you know, we conduct an experiment okay, and you know, we get volunteers with breast cancer, and then give some of them the experimental medication. Okay, and then let's say we had 20 people in our study. So let's say we have 20 people in our study. Okay. All right, and we see results in these 20 people. Okay. If the based on these 20 people, can we say anything about the general population? Okay. Or technically, we have to think, you know, who who is relevant to this research question, okay? So we're going to define something called the population. Okay, and so the population, and this is an important definition, the population is everyone or everything who is relevant to our research question. Okay, so if our research question is a new experimental medication more effective at treating breast cancer patients than currently existing treatments, who is the relevant population, or who is the population here? It would be all people with breast cancer, right? All breast cancer patients. Okay, this would be the entire population. In our example, this is everyone. Would be everyone who is a breast cancer patient. Okay. And so, we're not asking about health people without breast cancer. Okay, so our question here is relevant only to those who have breast cancer, but that is still a very large group of people. Okay, we cannot hope to study every single person in this population. Okay, so the population, even though our population is limited to just those who have breast cancer in general, or in almost all cases, all situations, the population is too big for us to study directly. Okay. And certainly not everyone might want to be studied, but whether we could or can't, the population is generally too big for us to study. So instead of trying to study everyone in the population to answer a question, so instead of trying to study everyone in the population, to answer a question, we often deal with a sample. We will deal with a sample of data. Okay, so, so here is this big thing called the population. And this thing is too big. Okay, and so instead we're going to take a little piece. Okay, and this thing we're going to magnify. Okay, and this thing is called our sample. All right, and we study and observe the sample. And based on what we see in the sample, we will then try to make conclusions about the population. Okay? So I'm going to draw kind of a dotted line going back to the population. So this process of making conclusions, this is called statistical inference. Okay? And our conclusions could be we don't have enough data to make a conclusion, okay? Or maybe we do. Even though the sample is just a small chunk from the population, what we see in the sample might be enough to tell us something meaningful about the population, okay? So depending on what we see, we might be able to say, my sample tells me this about the population. Or the other conclusion could be, I don't have enough data to really say anything, okay? Or there isn't any evidence at this time to make a conclusion, okay? So we might be able to say, my data tells me that the population ... okay? Or we might have to say, okay, we currently, we do not have enough data or we don't have any evidence supporting some conclusion. Okay, so those are both possible outcomes depending on what we see, right? If you just study 20 patients, it might not be enough to say that, the cancer improvement rate is very different. Okay, perhaps if all 20 patients are miraculously cured of their cancer, then that might provide compelling evidence, okay, if all 20. But then, if it's something like, a different rate of improvement, it may or may not provide evidence at that time. And it all depends on a bunch of different things, okay? But does this kind of give you a big picture of what we're doing in statistics here, okay? And so in order for us to make this conclusion, in order for us to look at just a little piece of data or a little sample of data and then make conclusions about the population, there's a kind of a lot of stuff that goes into it, okay? And so so as far as statistical inference goes, let me just kind of give you a overview of the different pieces that work together for us to make for us to do statistical inference. Okay, so this will be kind of like a course overview. Okay. Okay, and so we're going to part 1 is going to be on descriptive statistics. Okay. Okay, in descriptive statistics, this covers several topics. It's kind of part of it is learning to summarize data. Okay, and so we'll call, when we summarize data, we use the term numeric summaries. Okay, also called just not the word, not the subject, but the thing called a statistic. So when you hear people say things like, I don't want to just become another statistic, or you're looking up sports statistics. Those are values, summary numbers that summarize maybe a phenomenon going on in a nationwide phenomenon, or going on in a particular sport or something like that. Okay. For example, in order to, I don't know if any of you followed basketball this past season, but there's a player, Steph Curry, and he had a very good season. Okay, during the regular season, he performed very, very well, and you can look at all of the games. But during the finals, the last 7 games, his performance was not as good. And there's all sorts of discussions about why or whatever happened. But the fact that he had a very good performance during the regular season, and the fact that his performance during the last 7 games were not as good, can be summarized with just a few statistics. We can say Steph Curry's points per game was this, or his shooting percentage. And these are just numbers that just kind of summarize one little aspect of a player's performance. Okay? Now you could watch all 82 games or all 7 games of the finals series or whatever it might be to try to get a better picture of what happened. But certain numeric summaries, just single values that say, points per game was this, or shooting percentage was this here and versus over here, can also give you an idea of, can just summarize a bunch of information into just simple numbers that give us an idea of what could have happened. Okay, and it doesn't capture the whole story. The only way to get the whole story would be to watch all of the games, but the little numeric summaries, or those statistics, are still useful in pointing out certain aspects there. Okay, so those are descriptive statistics. There's a bunch of different things for we'll look at numeric data and categorical data, and we'll talk about all of these things. And also, and so there's a lot to be covered in descriptive statistics. Okay. After we cover descriptive statistics, we're going to venture into probability. Probability tells us how likely or unlikely events are. Or I'll say certain results, certain outcomes. Okay. We'll get into probability, and after we learn probability, we will learn about probability distributions. Probability distributions, these are so for particular measurements, some measurements follow certain patterns. Okay, so some measurements or some variables follow patterns, and if we know the pattern, or if we know that a measurement follows a certain pattern, we can start talking about how likely or unlikely particular measurements are. Okay. Okay, so, and we'll discuss this later, but for example, when we talk about how tall people are, we know that human height follows somewhat of a certain pattern or certain distribution, okay? And we can say that, it's going to be quite common to find people who are between 5 feet tall and 6 feet tall, okay? Those are going to be, if someone says, can you help me find somebody who is between 5 feet tall and 6 feet tall? You'd say, no problem. We just got to find the next person, and there's a good chance that this person is going to be between 5 and 6 feet tall, okay? On the other hand, if because, from our own experience, we know that people who are over 7 feet tall is very rare, okay? And then so if somebody says, can you help me find someone who's over 7 feet tall? You're going to be like, okay, well, let me think of, maybe we can find you a basketball team or a volleyball team or places where we might encounter some really tall people or something like that, okay? But, finding someone who's over 7 feet tall, that's going to be a tough thing to do. And so we can say, the probability of someone being over 7 feet tall is very low. But the probability that someone's between 5 feet tall and 6 feet tall is quite high, and things like that, okay? And that's just one example. But, there's other things, and we can say, what's the probability that someone's blood pressure is this, or whatever. And that's all answered in probability distributions, okay? Once we understand probability distributions, we can talk about what we call sampling distributions. And sampling distributions basically apply a probability distribution to samples of data, okay? How likely is a particular sample of data? Okay. And once we understand that, we can go back to our knowledge of descriptive statistics, and we will tie that in with sampling distributions, and then we can perform statistical inference. Okay. And statistical inference is what I claim is the reason why we study statistics, in that we are trying to make conclusions based on limited data or based on a sample of data, okay? Okay, and this ties together our understanding of descriptive statistics and our understanding of sampling distributions, which is built on all these other things that we will cover, the probability and probability distributions, okay? So the midterm exam will cover kind of these first three chunks: descriptive statistics, probability, and probability distributions. And then after the midterm exam, we'll focus on sampling distributions and statistical inference. But this is kind of just an overview of where we are headed in this course, okay? Are there any questions? So far, so good? Okay. So there are a few things we have to talk about here, okay? So if we're going to try to make conclusions about the population based on a sample, there's a very important thing, and that is our sample has to be representative of the population, right? So we want to make conclusions about the population based on a sample of data. Okay. All right, just quick question. What is a population? The population is what? Population is everyone, okay? So the population is everyone relevant to the question, okay? So generally the answer to the question lies in the population, right? If we want to know, is some drug effective, more effective? Ideally, we could see if the drug is, how effective it is in the population, and that will give us the true answer to how effective it is, okay? But obviously, we can't do that, okay? So instead of the population, we deal with the sample, and what is a sample? Yeah, sample is just a selection, a small selection taken from the population, okay? So we want to make conclusions about the population, everyone, based on a selection of people, okay? So about the population, so we want to make a conclusion about everyone based on a selection. Now, if we want our conclusions to be valid, which is all the time, right? No one says, I want conclusions that are invalid. If we want our conclusion to be valid, okay, then our sample needs to be representative of the population. Okay, and so this is a difficult thing to pull off. Okay, so to get a representative sample is actually quite difficult. I'm sorry? Was there a question? No? Okay. All right, so to get a representative sample is a difficult thing to do. One method that should but is not guaranteed to do so, that should give a representative sample. Is called simple random sampling. Okay, or we might abbreviate it SRS. Okay, and with simple random sampling, we start with a sampling frame. Okay, and a sampling frame ideally is a list of everyone in the population. But this is actually, getting a list of everyone in the population is also a difficult thing to do, okay? So, if I just gave you as a homework assignment, get a simple random sample of people in the city of Los Angeles, you would first need a sampling frame, which is a list of everyone in Los Angeles, okay? What could you use for a sampling frame? What could you use for a list of everyone in Los Angeles? A phone book? Okay. How many of you are listed in a phone book? Yeah, probably not very many of you, okay? So if we were to use that as a sampling frame, there would be no chance for any of you to be selected. Yeah, Facebook might actually be a better thing to use now, okay? So a lot of you probably have Facebook, but not all of you, okay? But there's probably more people listed in Facebook with, if somehow we could get, if Facebook would give us, which they won't, but if Facebook would tell us, these are all the people who logged onto Facebook from a IP address located in Los Angeles, this might give us a better idea of who is in Los Angeles, but we probably don't have access to that. But again, not everyone has Facebook. Probably the best, okay, which again is not accessible to us, would be if somehow we could get all of the cell phone towers within Los Angeles. That should be relatively easy to obtain, all the cell phone towers, and if we could get all of the cell phones that ping a Los Angeles-based cell phone tower, okay? And probably, cell phone usage is probably well over 95% in Los Angeles, and so that would probably give us a pretty good idea of who is located in Los Angeles at a given time. But not everyone has a cell phone, so we'll miss a few people, and we probably don't have access to that cell phone tower data, okay? So hard thing to do, okay? But if we have a cell phone, if we have a sampling frame, which is a list of everyone in the population, we then draw at random, and at random means truly at random, closing your eyes and going down the list and saying, this one, and then this one, and then this one. That's not random, that's just arbitrary, okay? Random is using some kind of device to randomly select people, or cutting them, numbering them, and randomly picking numbers or whatever it might be. We draw at random people one by one. Okay, and what this results in is that all people in the sampling frame have an equal chance of being selected. And then all possible samples have an equal chance of selection. Okay, and what I mean by all possible samples have an equal chance of selection, that is, you can think of the lottery, okay? And with the lotto, yeah, I don't know, there's like 65 numbers or whatever, okay? And you randomly select 6 balls, and it's simple random sampling. They are just picking balls one at a time out of that, the lotto machine, okay? And that means every possible combination of lottery numbers has an equal chance of being selected. So the combination, 3, 14, 25, 37, 42, 55 has an equal chance of being selected as the combination 1, 2, 3, 4, 5, 6, okay, which might feel strange, but based on simple random sampling, they both have an equal chance of being selected. Okay, as we go on, we can think about data, the data that we collect. Okay, so we collect data, and we can think of data as information that we organize. Okay, and we have two types of variables. We have numeric variables, which tell us how much or how many. Okay, and then we have categorical variables. And they tell us what type or what kind. Okay. When we store our data, we want to store them in what we call like a data frame. Okay, and so we would store our data in a data table. And the way we organize our data table is that each row represents an observational unit. Okay, and each column is a variable. Right. And so, for example, maybe we'll have things like name, and we'll ask someone's age, and maybe their weight, and their sex, their hair color. Okay, so maybe we have Audrey, 24, 140, female, brown hair. Okay, and then we have Bill, 22, 180, male, blonde hair. Okay, etc., etc., etc. So we can have more stuff here. Okay, so as far as the variables go, so each row is an observational unit. And in this case, each observational unit is a person, okay? Okay, and each column is a variable. All right, and so as far as variables go, we can identify whether they are numeric or categorical. And so age is recorded in years, and so this is numeric. This tells us how many years this person has been alive, okay? The weight tells us how many pounds this person weighs, okay? the sex would be categorical. This tells us what it's a type or kind. Okay, this is categorical, and hair color would also be categorical. What color hair someone has. Okay, and and there's we could have males or females, or maybe someone who does not identify as either, or hair color can be brown, blonde, black. There's a wide spectrum of colors, and we might have to define exactly what counts as this hair color, but we are listing these, and these are not telling us exactly. We don't have a quantity of how much. Okay. And so this is how we would store data in a data table. Okay. Okay. There is maybe a question of how should we obtain data in the first place. Okay. How do we gather or collect data? Okay. And so there are different types of data, but first we might talk about anecdotal data. Okay. Anecdotal data or evidence. Okay, and this is kind of the with anecdotal data or anecdotal evidence. This is a kind of a story. I know someone who this happened to. Okay. Someone who did this and then this happened. Okay, or these are kind of like customer testimonials. Or or stories about things. Okay, and I'm not trying to discredit anecdotal evidence or data or things like that, but as far as we have it, from a statistical standpoint, there is not much that we can do with anecdotal evidence. Okay, so from a statistical perspective, okay, so there's just not much we can do with anecdotal evidence. So other ways we get data is with the observational study. Okay. And with an observational study, we observe our participants. And collect data. Participants. Okay. We generally try not to interfere. We do our best not to interfere with the participants' lives. Okay, and you know, ideally we collect all information that could be relevant to the thing we're studying. Collect information on all aspects relevant to the thing we study. Okay, and then we analyze our data to see if any associations can be drawn. Okay. All right. So at the end of the observational study, okay, we try to, we might find an association between a particular variable and the outcome that we are studying, okay? Okay. However, even if there is an association, this does not mean that one causes the other, okay? An association, however, does not mean that one thing causes another. That one causes the other. Okay, so association is not, from an observational study, we can never make cause and effect conclusions, okay? Now, it might be true that the things that you find associated, it might be true that there's a cause and effect relationship between those things, but we cannot make that conclusion from an observational study, okay? So, you know, you might do a study, you might be interested, you know, is there a link between sugary diets and an increase of type 2 diabetes or something like that, okay? And maybe you do a study and you find that people with high quantities of sugar in their diet, more of them develop type 2 diabetes than those who have low sugar diets, okay? And so we might say that there's an association. And it might very well be, there might very well be a cause and effect relationship behind that, okay? However, from the data, from the statistics study alone, we cannot make that conclusion. In order to make a conclusion about what causes the other, there needs to be a deeper understanding of the mechanics within the human body. Okay, we have to understand exactly what causes type 2 diabetes and things like that. But we can't make those cause and effect conclusions just from the observational study. So a silly counterexample would be, we can do a study across households in the United States, and we might see a relationship between square footage of a house, okay, this house and the size of the house, and academic performance of the children in that house, okay? And we would probably see some kind of positive relationship where children coming from houses that are large have higher academic performance than children coming from houses that are small, okay? And does it mean that the way to cure our problems in education is just to have the child live in a bigger house? Would that solve things? No, we know that's a silly thing. And what's going on there? Huh? Well, okay, so yeah, so there's, now we say economics, and there's kind of this, for better or worse, we kind of acknowledge that there is this phenomenon that families with larger houses or probably larger incomes generally have students that perform better. Families, and it's kind of this accepted thing that, wealthier students from wealthier families perform better academically than students from lower income areas. But the question there is also, is there a cause and effect relationship between money and education or academic performance? Probably not in of itself. Probably money in of itself is not the answer, and things are just much more complicated as far as, how do we bring up academic performance, across the board. It's a complicated thing. Money is one aspect, but also just the quality of teachers in a certain area. It's it's complicated, right? Areas with generally higher income are able to attract certain teachers and keep higher quality teachers. That's part of it. Also, who knows? It's very complicated, and so just from an observational study, it's difficult, or it's actually not possible to draw exact cause and effect conclusions. But we can say that yes, there is some kind of relationship. There is some kind of link between these things that we're observing. But what's the answer? What is causing what? It's hard to know. Okay. So if you want to know what causes what, you would have to do an experiment. So an experiment is another way to gather data. And we might call this a controlled experiment. Okay, and with a controlled experiment, the researcher attempts to control as many aspects of variation as possible. Okay. So anything that could be related to the outcome that you're studying, whether it's academic performance or whether it's the risk of type 2 diabetes, anything that could be related to that outcome, ideally the researcher can control. Okay? So ideally, researcher can control everything related to the outcome. Okay, and then the researcher will assign randomly assigns certain conditions, or what we call treatments, to different groups of participants. Okay, so ideally everything for everyone, so all participants ideally will have the exact same set of conditions except for one thing, and that's the different treatments. Okay, so in the ideal scenario, everyone has the same conditions okay, except they differ in the treatments. Okay, so for example, let's say we were interested in does higher intakes of sugar, does that cause higher risk of type 2 diabetes? Okay, let's say we were interested in that. Okay, so ideally we would get a bunch of volunteers for our study, and we would say, okay, everyone is gonna now get the same amount of sleep. Everyone's gonna have the same amount of stress in their life. You know, we might be able to screen our participants so they have very similar genetics, they have similar age groups or age ranges, okay? So it's not just old people or young people or whatever, you know. Maybe we get volunteers so, you know, they have similar genetic backgrounds, similar ages, similar exercise habits, all of these things. And then the only thing that differs from one group to another is that this group gets lots of sugar in their diet and the other group does not, okay? And then at the end of the study, if we find that this group has a lot more people with type 2 diabetes and this group has a lot fewer, we can say, well, everything about these people were exactly the same except for the sugary versus non-sugary diets, and therefore the difference in type 2 diabetes can be attributed to the diet, okay? And that's how the experiment would work, okay? So at the end of the experiment, okay, differences between groups can be attributed to the different treatments. Okay, so with experiments you can make cause and effect conclusions. From an experiment. Okay, but experiments are not always ethically possible, okay? I don't think people would be happy if we said, okay, thanks for signing up for the duration of the experiment. We're going to just give you candy for breakfast, lunch, and dinner and see if that has an effect on your health, okay? It's not, or, you know, maybe we want to know the effects of long-term marijuana use, okay? We can't say, thanks for signing up for the experiment. Guess what? Starting tomorrow, you're going to use marijuana every day for the rest of your life, and then we're going to see what effects it has on your health. And people probably, that, you know, some people might be okay with that, but a lot of people probably would not be okay with being told what to do, okay? And in an experiment, you're basically telling people what to do, and so because of that, it's not always ethically possible, okay? So many experiments ethically or practically possible. Okay, and so, you know, if you wanted to know if are there effects of long-term marijuana use on, you know, on the brain or something like that, the only way you can kind of get at what happens is through an observational study, okay? And you could, maybe you find people who've been using marijuana for a long time, and maybe you can study their brain, you know, doing some kind of MRI or CAT scan looking at their brain and see if there are differences between those people who've used marijuana for a long time versus those who have not. But then there's this question of, do these people, are their brains different because they used marijuana for a long time? Or was there something different about their brains to begin with that has kind of led them to use marijuana for a long time? And there's kind of this question of, who knows what causes what? And we might be able to say there's some kind of link or association, but it doesn't necessarily answer the question that we originally have, which is what kind of effects would long-term marijuana use have on the brain? Okay, and as some states are considering whether or not to legalize the use of marijuana, these are questions that that need to, that probably people are curious about, and without experiments, it's hard to do. Okay, the long-term effects of using alcohol or large quantities of alcohol are now known because we've studied the mechanisms on how these things work. And so we have observational studies that support basically our understanding of from other fields of biology and anatomy and things like that. We understand how alcohol works in the body, and so we can understand that it causes the liver to work harder, and these things may have an effect, and the observational studies support that, but the observational study in of itself does not allow us to draw cause and effect conclusions. Okay, we'll pause here and we'll come back and get into some chapter 2 stuff and wrap up a few things in chapter 1. We'll also have kind of this diagnostic quiz to kind of just see how you're doing with your background math. Okay?